This project aims at addressing the challenges in accurately diagnosing ocular diseases, a crucial step towards improving patient care in the medical field. The core of my project is centered on the meticulous construction and evaluation of CNN models, wherein I leverage Python and Google Colab for an efficient and collaborative development environment. The dataset was sourced from Kaggle and encompasses a wide range of ocular images, which enabled me to train the models with real-world data. In this presentation, we'll handle complex ocular disease patterns and multi-classification challenges, by utilizing a range of algorithms from basic machine learning algorithms through to advanced CNN models and finally models utilizing transfer learning with VGG16. Specifically within this presentation, I will be highlighting the implementations of a starter CNN model, a more advanced CNN model, and finally the most optimized CNN model that utilizes a VGG16 transfer learning model as its base. Specifically, I address two key problems. First, the rich tapestry of patterns and manifestations inherent in these diseases requires a profound comprehension of ocular anatomy and pathology to accurately discriminate between them. And second, the multi-classification nature of the task, given the diversity of ocular diseases, which demands me to narrow my focus down to 4 classes. For this project, I adhere to the principle of alignment. I recognize that the intricate patterns presented by ocular diseases pose unique challenges. My insights lead me to develop robust models that can decipher these patterns, which serves as a testament to my aptitude for creating well-aligned machine learning models. In terms of my reflections, I emphasize practicality. I understand the essential role of practicality in addressing the complexities of multi-classification within ocular disease recognition. I ensure my efforts are calibrated to directly meet the practical demands of the medical community by engineering a model that produces accurate and usable results. My project aims to achieve 2 primary objectives. First, I develop robust CNN models for ocular disease recognition. This involves building models that not only achieve high accuracy but also demonstrate strong generalization capabilities, which I enhance through L2 regularization techniques. Secondly, as a secondary objective, I explore the potential of transfer learning to further improve performance. Specifically, I investigate the use of the VGG16 model, aiming to leverage its pre-trained features and fine-tuning strategies. This exploration of transfer learning, which could be considered an L3 capacity, is intended to assess its ability to enhance the accuracy and generalization of my ocular disease recognition system, building upon the robust models I initially developed. To begin, the foundation of my project lies in the ocular disease recognition dataset. This dataset is particularly valuable as it represents real-world medical data, meticulously collected by Shandong Medical Technology Company, Limited, from diverse hospitals and medical centers across China. What's crucial to note is the dataset's variability. FUNDUS images were captured using different camera brands, including Canon, Zeiss, and Kowa. This heterogeneity results in a wide range of image quality, mirroring the challenges encountered in actual clinical settings. Therefore, this dataset allows me to train and evaluate my models on data that is both diverse and representative of the complexities found in real-world scenarios. Now, having laid the groundwork with our objectives and dataset, I'll walk you through the core implementation steps I followed in this project. This process unfolded in 6 distinct phases. First, in Phase 1, I focused on data collection and pre-processing. This involved gathering a diverse dataset of ocular images, encompassing various diseases, and then meticulously pre-processing this data to standardize formats and enhance the efficiency of model training. Moving into Phase 2, I shift my attention to machine learning exploration. Here, I explore traditional machine learning models, such as random forest, SVM, and KNN, to establish a baseline performance and understand the inherent challenges of the data. Finally, in Phase 3, I design a starter CNN model architecture. This involves creating a simple convolutional neural network, which serves as a foundation for capturing basic features and sets the stage for the more advanced models I later develop. In Phase 4, I focus on advanced CNN model architecture, wherein I design and implement a more complex CNN architecture, aimed at achieving in-depth feature extraction and overall improved model performance. Following this, in Phase 5, I explore transfer learning with VGG16. I leverage the pre-trained VGG16 architecture to see if transfer learning can enhance performance further. Finally, in Phase 6, I move into the evaluation stage. I rigorously evaluate the models based on key metrics, including accuracy, loss, precision, recall, and F1 score. With the implementation phases outlined, I now want to delve into the specific architectures I developed, starting with the foundational starter CNN in Phase 3. This model serves as my initial exploration into advanced CNN concepts, and its design is crucial for understanding the subsequent refinements. The starter CNN architecture overview encapsulates the basic building blocks I use. It features convolutional layers to detect intricate image features, pooling layers to downsample data and manage complexity, a flattened layer to prepare data for dense layers, and dense layers to introduce nonlinearity for capturing complex data relationships. Finally, the output layer is designed for multi-class classification, using softmax activation to generate class probabilities. And importantly, I carefully consider model compilation, choosing the atom optimizer and categorical cross-entropy loss function. I then move to Phase 4, where I develop a more advanced CNN architecture. This phase focuses on significantly improving performance through the implementation of complex concepts. I make multi-layered convolutional blocks to enhance feature extraction with multiple CONV 2D layers in each block. Pooling and dimension reduction are achieved via max pooling layers to retain critical information while reducing spatial dimensions. Stabilization with batch normalization is added after max pooling to promote stability and faster convergence. To combat overfitting, strategic dropout is implemented at various points, with rates adjusted for optimal effect. A heavy regularization approach is adopted in the final block, with increased dropout rates. Flattening and dense layers facilitate efficient feature extraction, utilizing ReLU activation. Finally, the output layer is designed for multi-class classification with softmax activation. And, as before, I compile the model with the atom optimizer and categorical cross-entropy loss to ensure efficient learning and accurate multi-class classification. And here, you can see a visual representation of the advanced CNN model I implemented. The process begins with multiple CONV 2D layers, designed to capture the initial, intricate features within the ocular images. Following these convolutional layers, we have max pooling 2D layers. These layers effectively downsample the feature maps, reducing the spatial dimensions while retaining the most critical information. Think of it as summarizing the most important aspects of the image at that stage. Immediately after max pooling 2D, batch normalization is applied. This step is crucial for stabilizing the learning process, allowing the model to converge more quickly and efficiently. Imagine it as a way to ensure the data flowing through the network remains consistent and well-behaved. This pattern, as you can see, repeats several times. We have another set of two CONV 2D layers, followed by another round of max pooling 2D and batch normalization. This repetition allows the model to progressively learn more complex and abstract features as it moves deeper into the network. As the architecture narrows, you'll notice the layers becoming thinner and longer. This visually represents the dimensionality reduction happening as we move from spatial feature extraction towards the final classification. The data is being transformed from a 2D image representation into a 1D feature vector, preparing it for the fully connected layers that will make the final classification. Here, you can see the code snippet that defines the advanced CNN model architecture. And so, as we move towards the final stages of the network, specifically after the final convolutional block, the feature maps are flattened using layers.flatten. This transforms the 3D feature maps into a 1D vector, with a shape of none 4608, as you can see in the model summary. This flattened vector then feeds into the dense layers. I employ a dense layer with 1024 units and ReLU activation, as shown in layers.dense. 1024, activation equals ReLU, kernel_regularizer equals L2, 0.0001. Crucially, I also apply L2 regularization using kernel_regularizer equals L2, 0.0001, to prevent overfitting. Following this, I add another layers.batch normalization, and a layers.dropout, rate equals 0.5, for further regularization. Finally, the output layer is defined by layers.dense, for activation equals softmax. This layer has 4 units and uses softmax activation, which is ideal for our multi-class classification task, where we distinguish between 4 different ocular disease classes: The model is compiled using the atom optimizer and categorical cross-entropy loss, as these choices are well suited for efficient learning and multi-class classification problems. With the advanced CNN architecture detailed, I now move to Phase 5, where I explore the potential of transfer learning to further enhance performance. This phase centers around leveraging the VGG16 model, a powerful pre-trained architecture, to see if it can accelerate and improve our ocular disease recognition system. First, I imported the pre-trained VGG16 model from Keras. Then, I configured VGG16 for feature extraction, ensuring I capitalized on its pre-learned features. To preserve the integrity of these features, I froze the VGG16 layers. Building on this foundation, I designed a custom CNN model, essentially adding VGG16 as the base. To further tailor the model to the specific task, I integrated additional convolutional layers to enhance feature extraction. I then introduced dense layers with varying neuron counts and activation functions to capture complex relationships within the data. To prevent overfitting, I applied dropout layers for regularization. The output from the convolutional and dense layers was then flattened to one dimension for further processing. Finally, I added a final output layer for multi-class classification. And as with our previous models, I compiled the model using the atom optimizer and categorical cross-entropy loss, ensuring it's optimized for our multi-class classification. This slide depicts the VGG16 architecture, a convolutional neural network vital in computer vision. The yellow section on the left represents the input layer. This layer receives images, typically size 224 by 224 pixels with 3 color channels. Progression through the network reveals a pattern of red blocks followed by teal blocks. The red blocks are convolutional layers, CONV2D. These extract features from the input image by applying a series of filters, learning patterns and edges. Following each set of convolutional layers are the teal blocks, representing max pooling layers, max pooling 2D. These downsample feature maps, reducing spatial dimensions. This action aids computational efficiency and enhances the network's robustness to input variations. Observe the reduction in feature map size from left to right. This results directly from the max pooling layers. Also, note the increasing number of red blocks deeper into the network. This signifies the growing number of filters, enabling the network to learn more complex features. The initial red CONV2D block, immediately after the VGG16 base, signifies the introduction of a further convolutional layer with 256 filters, enhancing feature extraction. The subsequent teal max pooling 2D block downsamples these features, reducing dimensionality. The series of blue dense blocks, interspersed with dark teal dropout blocks, represent the fully connected layers. These dense layers progressively reduce the number of neurons, refining the learned features. The dropout layers, shown in dark teal, prevent overfitting by randomly deactivating neurons during training. The yellow flattened block, positioned before the final classification stage, transforms the multidimensional output of the convolutional layers into a one-dimensional vector, preparing it for the dense layers. Finally, the concluding blue dense block represents the output layer, with 4 neurons and softmax activation, generating probabilities for each of the 4 classes. This visual breakdown, coupled with the code implementation, demonstrates how I've adapted the VGG16 model, effectively transferring its learned features and customizing it for a specific classification problem. The non-trainable nature of the initial VGG16 segment, as shown in the model summary, is crucial for transfer learning, allowing me to leverage pre-existing knowledge without retraining those core layers. In my pursuit of optimal model performance, I explored and implemented a range of optimization techniques. To ensure model stability and accelerate convergence, I utilized batch normalization. Early stopping was employed to mitigate overfitting, halting training when validation metrics plateaued. I implemented L1 and L2 regularization for weight decay, enhancing the model's ability to generalize. Dropout layers were strategically placed to improve model robustness by randomly disabling neurons during training. A learning rate scheduler was used to dynamically adjust the learning rate, aiding convergence. I also implemented model checkpointing to save the best performing model, preventing data loss. While image augmentation was explored, it yielded limited accuracy improvements and primarily increased training time. Consequently, it was not incorporated into the final model. After the training phase, I obtained the following results for each model. The random forest model achieved an accuracy of 75.3%. While it demonstrated a precision of 67.83%, it faced challenges with recall and F1 score. The SVM model attained an accuracy of 72.74%, exhibiting balanced precision and recall with an F1 score of 58.05%. The KNN model achieved an accuracy of 70.72% but struggled with precision, recall, and F1 scores. The starter CNN showed progress with an accuracy of 77.63%. It reached a precision of 79.91%, but recall and F1 score remained challenging. It also incurred a loss of 70.27%. The advanced CNN demonstrated substantial improvement with an accuracy of 85.44%. It showed balanced precision, 76.71%, and recall, 70.41%, resulting in an F1 score of 72.25%. The loss was lower in comparison to the starter CNN model at 67.72%. Finally, the CNN plus VGG16 model emerged as the top performer with an accuracy of 88.68%. It maintained strong precision, 82.84%, and recall, 68.59%, resulting in an F1 score of 72.09%. Notably, the model had the lowest loss coming in at 37.01%. These metrics provide a comprehensive view of the performance and highlight the effectiveness of the CNN plus VGG16 model. I observed that the application of deep learning, particularly convolutional neural networks, significantly enhances the accuracy and precision of ocular disease recognition. Secondly, simpler models like random forest, support vector machines, and k-nearest neighbors provided a baseline, but were consistently outperformed by more complex CNN architectures. Thirdly, the advanced CNN model and the VGG16-based model achieved remarkable results, with accuracy exceeding 85%. These findings are promising and highlight the potential impact on the medical field. Finally, I discovered that transfer learning, exemplified by the integration of VGG16, introduces a new dimension to the project. It not only improves classification performance but also expands our understanding of model architectures. In conclusion, this project exemplifies the promising intersection of AI, deep learning, and healthcare. I have successfully employed advanced CNN models to accurately and reliably classify up to 4 diseases from the ocular disease recognition dataset. Overall, my findings and achievements emphasize the transformative potential of these technologies and the critical role they can play in medical diagnostics.